Hello my friends and welcome back to the You Can Do TV channel. Andritz Corporate is a leading force in the open die forging industry, with an annual production capacity of 75,000 tons. Its portfolio includes shafts, flange shafts, mandrel bushes, discs, and forged round bars, all produced to meet the highest technical standards. The facility operates one of the world's most advanced radial/axial hot rolling plants, capable of manufacturing rings up to 8,000 millimeters in diameter, 4,000 millimeters in height, and 140,000 kilograms in weight. Andritz integrates ultra-low emission regenerative burners to minimize environmental impact, while reinforcing technical expertise through over 2,000 hours of annual refresher training. The company also supplies critical components such as steam generators, shells, torus spherical heads, and tube sheets, consolidating its role in heavy industrial applications worldwide. Processing capabilities are supported by 22 band sawing machines with a maximum length of 63,000 millimeters, and a dedicated sawing system handling parts up to 500 millimeters and 250 tons. The machining division is equipped with 5 parallel lathes up to E2 800 millimeters by 22,000 millimeters, and 2 vertical lathes up to E4 300 millimeters by 2 800 millimeters, ensuring precision across a wide dimensional range. For over a century, aluminium has been at the heart of Scotland's industrial story. When the Lochaber smelter was built in the 1920s, it became the jewel of British Aluminium's operations. Its success was made possible by a remarkable hydroelectric scheme stretching across 90 miles of the Highlands, linking locks through tunnels, dams, and channels. Inside the pot rooms, alumina refined from bauxite arrives by rail and is transformed through electrolysis into molten aluminium. At the heart of the process, alumina derived from bauxite is delivered by rail and introduced into electrolytic cells. The powdered alumina is dissolved in a chemical bath, and a powerful electrical current passes through carbon anodes, separating pure aluminium, which sinks to the base of the cell. This electrolytic reduction requires significant energy, supplied by Lochaber's hydro system. Anodes are consumed during the reaction and are systematically replaced, with spent materials recycled. Advanced monitoring systems ensure that emissions, including carbon dioxide, remain tightly controlled. The molten aluminium is transferred to casting facilities where it is alloyed, refined, and cast into billets, slabs, or ingots depending on customer requirements. This stage enhances performance properties such as strength, durability, and corrosion resistance. Aluminium's recyclability and light weight make it essential in automotive and industrial applications. Although capacity is modest compared to global smelters, Liberty's investment aims to increase value by integrating an auto components plant directly on site. By transforming molten aluminium into finished parts without remelting, the facility reduces environmental impact and energy consumption. Combining century-old hydro infrastructure with modern technology, Lochaber remains a benchmark in sustainable aluminium production. From raw metal to precision engineering, the journey of an aluminium tube is both a test of science and a triumph of technology. What starts as a billet in the casting house will soon become a high-performance tube, forged under immense pressure, shaped with micrometric. The production of an aluminium tube begins with the remelting of raw aluminium. This process takes place in a furnace operating at approximately 800 degrees Celsius, where up to 12 tons of molten aluminium are held at a time. To guarantee material consistency, samples are regularly taken and analyzed in the laboratory to verify chemical composition. Once the alloy meets the required specifications, the molten aluminium is cast into molds, solidifying into billets. The billets, once cooled, are cut to size according to customer requirements. Before extrusion, they are preheated to around 500 degrees Celsius in a billet heater, ensuring optimal plasticity. The hot billet, together with a pressure disc, is loaded into the press container. A mandrel pierces the billet, and then the main ram applies a force of nearly 4,000 tons, extruding the aluminium through a die and over the mandrel. The result is a hollow tube exiting the press at more than 500 degrees Celsius. Excess material is collected and returned to the cast house for recycling, minimizing waste. At this stage, the extruded tube does not yet meet precise dimensional requirements. In the drawing shop, the tube is prepared for cold drawing. It is pushed onto a drawing bar fitted with a plug, lubricated, and pulled through a drawing die. This process simultaneously reduces the outer diameter and wall thickness, achieving the specified geometry with tight tolerances. However, the tube's mechanical properties remain insufficient for demanding applications such as automotive shock absorbers. To improve strength and hardness, the tube undergoes solution heat treatment in a tower furnace at over 500 degrees Celsius, followed by rapid quenching in water. Straightening operations are then performed to guarantee accuracy, eliminating distortion. Subsequently, the tube is aged at 170 degrees Celsius to achieve the final temper. Once heat treatment is completed, the tubes are cut to the required lengths. Rigorous inspection follows, particularly for the internal diameter, where tolerances are limited to 0.08 millimeters. This ensures uniform wall thickness and consistent performance. The end result is a high-strength aluminium tube, lightweight yet almost as strong as steel, ready for use in shock absorbers and other engineering applications. Through each stage, casting, extrusion, drawing, heat treatment, straightening, and final inspection, the process demonstrates the combination of advanced metallurgy, precision engineering, and recycling efficiency. The outcome is a reliable, dimensionally accurate aluminium tube that meets stringent industry requirements while delivering the essential benefits of lightweight strength. The Andritz workshop demonstrates advanced capabilities in upgrading screw presses, delivering higher performance, longer service life, and cost efficiency. The process begins with the shipment of existing components to the Andritz facility, where each part undergoes a detailed inspection and assessment. Key elements are then selected for refurbishment, while new components are engineered to meet updated design and operational requirements. At the core of the upgrade, a newly modified screw flight is installed, reinforced with advanced wear protection to maximize durability under demanding operating conditions. Existing screen baskets are carefully refurbished to restore their structural integrity and functionality, while additional new screen baskets are incorporated to optimize throughput and reliability. Other supporting components are overhauled and reconditioned for reuse, ensuring a sustainable approach that balances performance improvement with resource efficiency. By combining refurbished elements with state-of-the-art replacements, Andritz delivers a tailored solution that not only restores but significantly enhances press performance. This systematic upgrade process highlights the company's technical expertise, precision engineering, and commitment to extending the life cycle of critical equipment while minimizing downtime for operators. Bays. Electric motors are at the heart of modern industry, providing the driving force for machinery ranging from small appliances to massive overhead cranes capable of lifting hundreds of tons. In these demanding environments, precision, strength, and reliability are not optional, they are essential. Companies such as Conesco manufacture a wide spectrum of motors, from compact units no larger than a coffee mug to giants weighing more than 2.5 tons. Despite differences in size and application, every electric motor shares the same fundamental components and principles: a shaft, a rotor, a stator, bearings, end shields, a frame, a brake system, a fan for cooling, and a conduit box for power connection. Understanding how these parts come together reveals the complexity and craftsmanship behind each motor. The creation of an electric motor begins in the raw materials warehouse. Steel rods, carefully selected according to the motor's design, are cut to precise lengths on a cutting line. These rods will eventually become the motor's shaft. Once cut, the steel pieces undergo extensive machining on computer numerical control systems, or CNC machines. Through turning, shaping, and cooling with emulsion, the rod is transformed into a highly accurate shaft, ready to transfer rotational energy within the motor. Meanwhile, on the other side of the factory, sheets of electrical steel are stamped into laminations. These thin metal blanks are divided into two types: stator laminations and rotor laminations. The stator laminations are stacked and welded together to form the stationary core of the motor, while the rotor laminations are stacked and cast into a solid structure. To complete the rotor, grooves between laminations are filled with molten aluminum. This casting process, though it appears simple, requires flawless execution. If the molten metal is poured unevenly, air bubbles can form, compromising the structure. Cooling too rapidly can create shrinkage voids, while high humidity introduces water into the aluminum, breaking it into hydrogen and oxygen that form gas pockets and slag. Precision in timing, temperature, and environmental conditions is vital. After cooling, the shaft is pressed into the rotor assembly. The outer surface of the rotor is then turned on a lathe to achieve the exact diameter required. Accuracy here is critical, as the rotor must rotate smoothly within the stator with only a 0.3 mm clearance, thinner than a business card. Any deviation could compromise performance or cause damaging contact at high speeds. Once sized correctly, the rotor is dynamically balanced, and ball bearings are mounted to allow smooth rotation during operation. Attention then shifts to the stator, which undergoes the most labor-intensive phase of motor production, winding. First, the slots of the stator are insulated with sheets of dielectric paper made from specialized materials such as Nomex and Mylar. This insulation prevents electrical shorts and withstands the high thermal stresses generated during operation. Next, enamel-coated copper wire is wound into precise coils and inserted into the insulated slots. These coils form the motor's electromagnetic field, converting electrical energy into mechanical torque. Once in place, the coils are connected, terminated, and laced to secure them firmly, preventing vibration during use. Depending on the size of the motor, winding can take anywhere from 2 hours to 2 full weeks to complete. Every wound stator is then rigorously tested. Only those meeting strict standards move on to impregnation. Vacuum pressure impregnation is a process in which the wound stator is submerged in resin inside a sealed pressure tank. Through a series of pressure and vacuum cycles, the resin penetrates deep into the windings, coating each conductor and insulating material. The impregnated stator is allowed to drip dry, then cured under heat to harden the resin. This process transforms the winding assembly into a solid, durable, monolithic structure. The benefits are significant: improved thermal conductivity, enhanced dielectric strength, increased mechanical stability, reduced maintenance needs, and longer service life. Once impregnation is complete, the stator receives its housing. Depending on motor design, the frame may be cast from iron or aluminum. Aluminum housings are heated to around 200 degrees Celsius for up to half an hour, causing the metal to expand. The heated housing is then slid over the stator. As it cools, the metal contracts and grips the stator tightly without requiring fasteners. This interference fit ensures a strong, vibration-resistant assembly. At this point, all major components are ready and final assembly begins. Engineers gather the shaft, rotor, stator, bearings, fan, brake, and conduit box at an assembly station. Following detailed engineering drawings, each element is precisely installed. The rotor is carefully aligned within the stator, bearings are secured, the cooling fan is attached, and protective end shields are mounted. The conduit box is fitted to allow electrical connection. Each assembly step requires both skill and discipline, ensuring that tolerances are maintained and no detail is overlooked. After assembly, every motor undergoes final inspection and testing. At Kinesco, more than 90,000 motors are manufactured annually, and each is tested individually. The tests simulate real-world operating conditions, applying electrical load and mechanical stress while monitoring performance. Critical parameters such as vibration, noise, efficiency, and thermal behavior are measured. Results are documented and archived, guaranteeing full traceability. Only motors that pass these rigorous trials proceed to customer delivery. For motors with aluminum housings, testing marks the final stage. Cast iron housings, however, require an additional finishing step. After priming with a white undercoat, the motor is painted according to client specifications. Standard industrial colors are often used, but custom finishes are available when branding or visual identity is important. When large orders are placed, production may be transferred from manual assembly to automated lines. In these cases, advanced robotics handle nearly every stage, from cutting and stamping laminations to winding coils, impregnating stators, and assembling components. Automation improves consistency and throughput, though skilled technicians remain essential to oversee quality control and handle specialized or custom builds. The journey from raw steel rods and sheet metal to a finished electric motor is long and meticulous. It involves machining, stamping, casting, winding, impregnation, housing, and final assembly, with each step demanding precision. The result is a machine capable of extraordinary reliability and power, able to move massive loads with precision, or run quietly for years in everyday equipment. Electric motors may appear simple on the outside, but their construction represents a fusion of science, engineering, and craftsmanship, ensuring they remain the beating heart of modern industry. GE Hydro Solutions Bilbao workshop focuses on advanced technical expertise, servicing stators and rotors up to 250 megawatts. With an engineering excellence center, precision pull coils, and 3,000 square meters dedicated facilities, it ensures extended life and performance of hydropower equipment. UN. In the early 1970s, Rolls-Royce faced one of the most critical chapters in its history, with the development of a revolutionary engine for the Lockheed TriStar, one of the world's first jumbo jets. At that time, the Derby facility was relatively small by global standards, producing engines in limited volumes. The RB211 engine represented a bold leap in technology. It was the first three-shaft turbofan design, while competitors relied on simpler two-shaft systems. This new architecture promised reduced weight, higher efficiency, and lower operating costs, factors that were expected to transform air travel through cheaper fares and improved performance. However, translating advanced design into production proved more challenging than anticipated. Development costs spiraled as engineering teams pushed the limits of technology. Despite setbacks, the first successful test run of the RB211 in February 1971 demonstrated outstanding results, outperforming all previous prototypes. Once installed on the Lockheed TriStar, the engine proved its worth. Its advanced architecture became the foundation of a new generation of jet engines, later evolving into the Trent family, now powering half of the world's large passenger aircraft. This success propelled Rolls-Royce from a modest manufacturer into a global leader in aerospace propulsion. Today, the Derby plant remains at the heart of Trent engine production. The assembly line is organized with precise scheduling, taking 20 days from initial component preparation to a fully completed engine. Production begins with the assembly of complex internal modules, including hundreds of precision-machined blades. Each component is hand-fitted to exact tolerances, ensuring aerodynamic perfection. By the fourth day, work begins on the Kevlar-wrapped aluminum fan case, followed by the integration of more than 4,000 control and transmission parts. Expert fitters then undertake the 9-day process of assembling the 8 major engine modules. The lower sections are stacked vertically, with gravity aiding precise alignment, while critical couplings are installed with delicate adjustments to avoid damage. By the end of the first week, the massive fan is assembled, each blade valued as highly as a family car. Extreme care is taken during installation, with workers wearing gloves to protect the polished surfaces. The fan is then mounted into position with clearances measured in fractions of a millimeter, despite the fact it will rotate at supersonic speeds during flight. Once assembly is completed, each engine undergoes rigorous testing at the factory's dedicated facility. Trials simulate the most demanding flight conditions, monitoring vibration, temperatures, and rotation speeds. Specialized safety tests include cold starts at -40 degrees Celsius, water ingestion trials with 30,000 gallons of water per hour, and even explosive fan blade release experiments. The latter ensures the containment case can withstand forces equivalent to dropping a 1-ton car from a 200-meter height. Though such tests destroy engines, they are essential to guarantee passenger safety. Modern Trent engines are further enhanced with a network of advanced sensors. These devices monitor temperature, pressure, vibration, and rotational speed in real time, transmitting data to the engine's onboard computer for optimized performance. Beyond flight, sensor data is relayed via satellite to the Derby Control Center, where engineers monitor the global fleet 24 hours a day. This continuous feedback allows predictive maintenance, rapid fault detection, and proactive service planning. Rolls-Royce has also transformed its business model with long-term service agreements. Airlines now purchase not only engines but also comprehensive support packages, often lasting 20 years. Under these agreements, Rolls-Royce guarantees maintenance, spare parts, and engine availability, while customers pay based on actual flying hours. This strategy strengthens customer trust while ensuring operational reliability worldwide. From the near collapse of 1971 to its present status as a global aerospace powerhouse, Rolls-Royce's journey with the RB211 and the Trent family illustrates how technological ambition, resilience, and government support reshaped the company. The innovations pioneered in Derby continue to define modern aviation, making the factory not only a center of precision engineering, but also a symbol of survival and success in the face of crisis. LM Wind Power made history by building the world's first wind turbine blade exceeding 100 meters, the LM 107.0P, measuring 107 meters, produced in Cherbourg, France. This achievement marks a leap from 17-meter blades in 1991, when the first offshore wind farm was born, to today's record-breaking offshore solutions. Over 30 years, LM has delivered blades powering 2.6 gigawatts of offshore capacity worldwide. Advanced material selection, optimized processes, and rain erosion testing ensure proven reliability and durability. Once built, the giant wing was specially transported to join a global testing program, confirming its industry-leading position. The HyFlex high-voltage coil insulation system by IPS Newcastle is designed to deliver reliability, durability, and precision for demanding electrical applications. Each project begins with dedicated technical account management, administrative support, and detailed project planning, supported by CAD functions to ensure accuracy from the start. Coil production follows a strict sequence, beginning with coil forming and section binding of the coil stack. The process continues with shaping, lead and althang taping, and machine taping of the main wall insulation, guaranteeing consistent quality and robustness. Once insulated, the coils are carefully fitted into a replica stator to verify alignment and functionality. Final pressing and tolerance checking ensure dimensional accuracy, while advanced electrical testing, including tan delta, high pot, and interturn tests, validates performance and safety. A rigorous quality control system monitors every stage to maintain compliance with international standards. For final delivery, high-voltage stator windings and coils are securely packed in moisture-proof export-grade packaging to protect against environmental damage. This integrated process ensures high reliability, long service life, and customer confidence worldwide. The manufacturing of large-diameter pipes follows a precise and highly controlled sequence of operations designed to ensure dimensional accuracy, weld integrity, and structural reliability. Manufacturing starts with numbering of the plates, where raw steel plates are identified and prepared for processing. Handling is carried out by a vacuum crane, which safely lifts and positions the plates at the start of the production line without surface damage. The next step is edge milling, where the longitudinal edges of the plate are machined to achieve a uniform bevel and precise geometry required for welding. Following this, the prepared plate enters the 3-roll bending machine, which progressively forms the flat plate into a cylindrical shape. To ensure stability, post-bending operations are applied, aligning the edges for accurate joining. Once the plate assumes the correct cylindrical form, it undergoes tack welding, a temporary welding process that holds the structure firmly in place. The pipe body then moves to the internal welding machine, where a continuous, full-penetration weld is applied along the inside seam. This is followed by external welding, performed by a dedicated machine to reinforce the joint from the outside. Both welds are critical for ensuring structural integrity and durability under pressure conditions. After welding, the pipe is subjected to visual inspection to detect any surface irregularities or defects. It then enters the pre-washing machine, which removes debris and contaminants prior to expansion. In the expander stage, the pipe diameter is mechanically expanded to achieve precise roundness, correct residual stresses, and improve dimensional consistency. This is followed by a post-washing process to remove any remaining residues from the expansion stage. Once integrity is confirmed, the pipe undergoes end beveling, where its ends are machined to the correct bevel angle to facilitate field welding and assembly. The pipe must then prove its ability to withstand operating conditions through a hydrostatic test. In this process, water pressure is applied internally to confirm the strength of the welds and the overall pipe body. Advanced, non-destructive evaluation follows, using ultrasonic weld detection technology to identify any hidden defects along the weld seam. Finally, a comprehensive inspection is performed, ensuring the pipe meets all dimensional, mechanical, and safety standards before release. This systematic sequence, from plate handling and forming to welding, expansion, testing, and inspection, ensures that each manufactured pipe is capable of meeting stringent requirements for oil, gas, water, and structural applications, delivering reliability under demanding operating environments. The integration of Cogsdill ZX tooling on the Doosan DBC 130 horizontal boring machine demonstrates a combination of advanced engineering, modular versatility, and uncompromising precision in metalworking operations. The process initiates with the attachment of the camlock bonnet, a robust interface system designed to secure the tooling to the spindle with absolute rigidity. By tightening the 4 camlock fasteners, the bonnet is locked in place, creating a stable connection that effectively eliminates vibration and ensures outstanding repeatability. This connection is fundamental to achieving an unrivaled surface finish, as the rigid interface prevents chatter and delivers a consistent machining environment, even under high load conditions. Once the bonnet is firmly attached, the ZX300 contouring head is prepared for operation. Prior to engagement, lubrication of the ZX300 is applied to ensure smooth functionality and durability of its mechanical components. The spindle speed is set to 150 revolutions per minute for initial bonnet rotation, and during contouring tasks, the ZX300 head can operate at speeds of up to 800 revolutions per minute. This precision-facing and contouring head allows accurate adjustment of cutting diameters, enabling fine surface machining and geometrical control across a wide range of applications. The ZX300 embodies the precision and repeatability that Cogsdill tooling is renowned for, delivering results with minimal need for secondary finishing operations. Following the contouring stage, the collet pilot is tightened to secure the internal tooling system within the spindle. At this stage, the modular boring tools, MBT, from Cogsdill are introduced. These modular boring heads are designed for internal bore machining, offering flexibility through interchangeable cartridges and pilot mechanisms. The MBT system supports a broad range of diameters and maintains extremely high accuracy, allowing for concentric and dimensionally stable bores. The use of a pilot system, typically incorporating coolant distribution, enhances machining reliability by maintaining tool alignment and optimizing chip evacuation. This results in consistent bore quality, making the MBT system suitable for demanding applications in industries requiring tight tolerance control. For larger facing operations, the Cogsdill ZX900 facing head may be utilized. This head is designed to handle extensive diameters with equal precision, enabling heavy-duty facing and contouring tasks without sacrificing surface integrity. The ZX900, when combined with the camlock bonnet interface, provides the stiffness required for machining operations on large components, a critical factor in industries such as aerospace, energy, and heavy equipment manufacturing. Together, the ZX300 and ZX900 form a versatile duo of contouring and facing solutions, adaptable to a wide range of machining challenges. The Cogsdill tooling suite extends further into specialized applications, including splining and milling heads, all of which integrate seamlessly with the Doosan DBC 130 HBM platform. This modularity allows operators to configure the tooling system for multiple tasks within a single setup, reducing downtime and increasing productivity. By minimizing the need for repeated machine resets, the system ensures greater efficiency and throughput while maintaining high-quality results. The advanced engineering of the bonded interface, combined with the modular flexibility of ZX tooling, establishes a system that maximizes spindle performance and maintains superior surface finish across all operations. Ultimately, the application of Cogsdill ZX tooling on the Doosan DBC-130 horizontal boring machine exemplifies the synergy between rigid mechanical interfaces, modular tooling architecture, and precision-driven machining processes. Each stage, from bonnet attachment and spindle calibration to contouring, boring, and large-scale facing, is engineered for reliability and accuracy. The result is a machining solution capable of delivering exceptional repeatability, outstanding surface quality, and unmatched flexibility in demanding industrial environments. B. In 1830, a traveling founder settled and established this workshop, beginning a tradition of bell casting that has continued for generations. Today, the same meticulous craftsmanship is preserved, with each bell defined by its size, weight, and most importantly, its note, the unique sound it will produce. Fabrication is initiated through a detailed plan. A partial design is drawn and transferred onto a wooden template, known as the trousseau. From empirical calculations perfected over centuries, this curve dictates the bell's acoustic qualities. The trousseau then guides the entire mold-making process. The mold consists of three main parts: the core, or inner shape, the false bell, which represents the exact profile of the future bell, and the outer shell, called the cope. Once the false bell is sculpted in clay, it becomes the model on which decorations, inscriptions, and religious motifs, cut from wax in the workshop, are applied. These details are then embedded into successive layers of fine clay, forming a strong outer shell that will capture the designs in perfect negative once the bell is cast. When the cope is complete, the false bell is destroyed, leaving the necessary cavity between the core and outer shell. The mold is then placed in a casting pit, carefully backfilled and compacted with earth. This serves two functions: to resist the immense pressure of molten bronze and to provide thermal insulation, allowing for slow cooling. This gradual solidification refines the grain of the metal, producing a stronger, more resonant bell. Bell bronze is a precise alloy of 78% copper and 22% tin. The metal is melted in a reverberatory furnace dating back to around 1840, which works by heating a vaulted chamber that radiates energy onto the molten bath. Once the alloy reaches temperature, tin is added, and the molten bronze is carefully guided via channels into the prepared molds buried beneath the earth. After the pour, the mold is left to cool over several days. When sufficiently solidified, the founder returns to excavate the bell, digging out the packed earth to reveal the cast form. At this stage, the bell may still retain some warmth, but it is chemically stable. The final steps are cleaning, refining, and most importantly, striking the bell for the very first time. That first strike, le premier coup de béton, is the culmination of nearly 3 months of work. It carries both technical precision and emotional weight, as the founder hears the sound that validates the entire process, a tone shaped by tradition, material science, and patient craftsmanship. Bremen Machinery, in collaboration with RB211 Trent, commissioned a new plate bending machine in mid-2009, a state-of-the-art 3-roll bending system with remarkable capabilities. Manufactured by Hössler in Switzerland, this massive 320-ton machine required a lead time of over 1.5 years, and the construction of a special reinforced foundation to support its weight and precision demands. The machine demonstrates exceptional flexibility in handling heavy plate rolling tasks. Before rolling, each flat plate is prepared with small overlaps at both ends. This preparation is critical, as it allows accurate formation of welding edges and ensures a precise circular outcome once the plate is bent. The edge preparation process must be carried out with the utmost accuracy to achieve a high-quality round result. Once the preparation is complete, the plate is marked carefully to guide the cutting process. Preheating ensures clean separation, and as the excess length is cut away, proper welding edges are simultaneously formed. With the plate cut to size, it is ready to be rolled into a cylindrical shell. In this demonstration, the rolled section achieves an external diameter of 2,076 millimeters. The welding of the rolled shells is performed using a highly productive submerged arc welding method. This process ensures rapid deposition rates, and in some cases, 2 filler wires are used simultaneously to speed up the filling of the weld seam. The wires are covered with a protective flux layer, and any excess powder is efficiently collected and reused, ensuring both quality and sustainability. Complementing this bending machine, RB211 Trent also operates one of Europe's heaviest press brakes, with a bending capacity of 3,000 tons over a working length of 8,000 millimeters. This press delivers an impressive force of 800 tons per meter, enabling the shaping of extremely thick plates. A notable example shown is the forming of a stainless steel plate measuring 60 millimeters in thickness and 7.2 meters in length, which is shaped into a precise radius. Finally, the machine demonstrates its power by rolling a colossal 43-ton steel plate, 150 millimeters thick and 2,230 millimeters wide, into a diameter of 5,000 millimeters. This striking example showcases the immense strength and precision that Bremen Machinery and RB211 Trent can deliver to meet the most demanding industrial applications. Hey! With nearly 4 decades of experience, SAWMISA has earned a reputation for delivering high-quality products and innovative technical solutions, particularly for sugar and ethanol production and cogeneration from sugarcane byproducts. Their product portfolio and technical expertise cater to both domestic and international markets, making them a trusted partner in the global agro-industrial sector. SAWMISA specializes in designing and manufacturing a wide range of equipment tailored to the needs of sugarcane mills. Their flagship products include sugarcane mills, moendas. SAWMISA is a market leader in Brazil for sugarcane mills, which are critical for extracting juice from sugarcane with maximum efficiency. These mills are engineered for durability and high performance, incorporating advanced materials and precision manufacturing to ensure optimal juice extraction and minimal downtime. Their designs are customized to meet the specific needs of each client, accommodating various mill sizes and processing capacities. Guincho Hilo. This innovative equipment is designed for receiving whole or chopped sugarcane, with capacities ranging from 35 to 50 tons. The Guincho Hilo streamlines the initial processing stage by efficiently handling large volumes of raw material, reducing operational bottlenecks and enhancing throughput. Cogeneration systems. SAWMISA provides equipment for biomass-based energy cogeneration, enabling sugarcane mills to generate electricity from bagasse, sugarcane residue, and straw. These systems support sustainable energy production, reducing reliance on fossil fuels and minimizing environmental impact. Their cogeneration solutions include boilers, turbines, and auxiliary equipment designed for seamless integration into existing mill infrastructure. Material preparation and juice treatment systems. SAWMISA offers specialized equipment for preparing sugarcane and treating extracted juice, ensuring high purity and efficiency in sugar and ethanol production. These systems are engineered to handle large-scale operations while maintaining strict quality standards. SAWMISA's technical solutions are underpinned by a commitment to innovation and precision engineering. These facilities are equipped with state-of-the-art machinery, including custom-built tools for manufacturing complex industrial components. The company invests heavily in research and development to stay at the forefront of industry trends. Their engineering team, composed of highly trained professionals, leverages advanced design software and simulation tools to develop equipment that meets rigorous performance and safety standards. SAWMISA's technical expertise extends to SAWMISA collaborates closely with clients to tailor equipment and systems to specific operational requirements. This includes optimizing mill designs for higher efficiency or adapting cogeneration systems to maximize energy output. Maintenance and upgrades. SAWMISA provides comprehensive maintenance services, particularly during the off-season, entre safra, to ensure equipment reliability and longevity. They also offer modernization services to upgrade existing plants, enhancing productivity and compliance with modern environmental regulations. With a presence in multiple countries, SAWMISA offers technical consulting and after-sales support, ensuring clients receive prompt assistance for installation, troubleshooting, and optimization. SAWMISA's technical solutions contribute to sustainability by enabling efficient energy cogeneration and reducing waste in sugarcane processing. Their equipment supports the production of renewable energy, aligning with global efforts to combat climate change. Since the 1990s, SAMISA has expanded its footprint internationally, supplying equipment and consulting services to sugarcane mills across Latin America and beyond. SAMISA's product portfolio and technical solutions reflect their deep expertise in the sugarcane, and offerings are designed to enhance efficiency, reliability, and environmental responsibility. With a robust infrastructure, innovative engineering, and a global outlook, SAMISA continues to drive progress in the agro-industrial sector, delivering value to clients worldwide.